Many landforms that are common all over the earth cannot be explained by slow processes of erosion over millions of years. Some people think, well, hasn't the flood been disproved? Even though we have all this evidence for the flood, hasn't it been disproved? No, no way it has been disproved. It was just assumed wrong and was rejected for unscientific reasons. A lot of us are bringing back the flood into Earth history. And you know something? We are finding solutions to many mysteries out there in the rocks, of which this series shows you mysteries from the field of geomorphology. The surface of the earth presents a lot of mysteries. These are mysteries to uniformitarian evolutionary geology because they can't explain them by slow processes over millions of years. Some of these, we call them landforms. They might be a mountain range, it might be a valley, it might be a planation surface, it might be a pediment, it might be a submarine canyon. You include the bottom of the ocean in geomorphology, by the way, the surface shape of the bottom of the ocean. Many landforms that are common all over the earth cannot be explained by slow processes of erosion over millions of years. For instance, one of the most significant landforms all over the earth are planation surfaces. Some of these planation surfaces are very large, like most of Africa is either one or a couple of planation surfaces that cover 60% of the continent. That's why it's so flat on Africa. Like the Serengeti is flat. You see animals moving on it on a flat plain, that's Serengeti. But look at the sedimentary rocks and metamorphic rocks below there. They go up like this, which means before they were plain flat, they used to go up like this, and then something just sheared them off. We don't observe planation surfaces forming today, except on a very small scale when a river floods the edge of the river and cuts maybe some tilted rocks possibly, erodes that flat. Otherwise, the scale of these is so huge you don't see them forming over large scales. But if we wanted to use the river as an analogy, look at the scale of the one in Africa. We would need a river the size of Africa. Well, what does this mean? Well, we're talking about the Genesis flood and the sheet erosion planing the land. As Africa was coming up, the waters were running off. It's the same with the other continents, but there was a lot more tectonics on other continents, so you broke up these planation surfaces that were once much larger by tectonics and erosion. So now you just have erosional remnants of planation surfaces. They're smaller. Like the high plains is a series of 4 planation surfaces caused by erosion. You had one level up here that covered the high plains of Canada, Alberta, and Montana, parts of North Dakota and Wyoming. It spread the resistant quartzites on these, and then most of it got eroded to where you have small remnants here and there. Like the Cypress Hills is the biggest remnant. It's about 1,000 square miles, capped by 75 feet of rounded cobbles that come from 400 miles away. And also, speaking of those cobbles, that's another big mystery in uniformitarian geology because they've been transported way too far for normal rivers. And in fact, in the high plains of Montana and Alberta and Saskatchewan, and even Manitoba, and even North Dakota, from the direction of the currents we can determine from the rocks and also the sand interbeds, they came from the southwest, which the closest location of quartzite in the southwest is in central Idaho, and that's across the Continental Divide. So if we had normal rivers depositing this, they'd have to come over the divide and get spread way out there. In fact, the furthest spread of these quartzites is 800 miles. And this is not an unusual pattern for the Northwest states and adjacent Canada. You see this pattern around other mountain ranges of the world. These are mysteries of how could this happen under millions of years of time. Also, pediments aren't being formed today. Submarine canyons aren't being formed. They're being modified. They're being deepened a little bit or filled a little bit, but that's all we observe. Water gaps and wind gaps aren't forming today except on a teeny scale, very small scale, but some of these water gaps are really deep. There can be a mile deep or 2 miles. Some coming through the Himalaya mountains up to 4 miles deep. In the Zagros Mountains are up to 8,000 feet deep. So these things are huge gorges cut through mountains. These are not forming today, and so they're huge mysteries trying to account for them. How does a river go uphill and cut that water gap? Well, they have a lot of ideas. There's usually evidence against these ideas out in the field. Well, the evidence shows that the flood can readily explain these features of geomorphology. Some people think, well, hasn't the flood been disproved? Even though we have all this evidence for the flood, hasn't it been disproved? No, no way it has been disproved. It was just assumed wrong and was rejected for unscientific reasons. And started back in the Enlightenment. Enlightenment started in the 1700s when intellectuals and scholars and educated laymen, they thought they can explain everything without the Bible. So they rejected the Bible, especially Genesis, creation and the flood, the Tower of Babel incident for the origin of the languages, and the short time scale of Scripture. They rejected all that. And therefore they had to explain all of earth science by processes going on today, present processes, or uniform processes they called it. That's why the idea became called Uniformitarianism. Uniformitarianism was developed by James Hutton, and also Charles Lyell embellished on it and actually made it more popular starting in 1830 and finishing in 1833 in 3 volumes of the Principles of Geology. Was this a conclusion of science at the time? No, they had a lot of crazy ideas of geology at the time, thinking the sedimentary rocks were the results of heat action. They knew hardly anything about geology, but they arbitrarily rejected Scripture, the flood, which has a lot to say about geology. The Bible is a history book. It goes into what happened in the past. And by the way, no scientist was there to observe this. So it's based on interpretation. So the interpretation became the Enlightenment interpretation, uniformitarianism, an arbitrary assumption that continues to this day. And the rejection of the flood was not because of science, it was because of personal rejection, arbitrary decisions, subjective decisions they made starting with the age of the Enlightenment. So a lot of us are bringing back the flood into Earth history. And you know something? We are finding solutions to many mysteries out there in the rocks, of which this series shows you mysteries from the field of geomorphology. Well, when we read Genesis, we divide biblical Earth history up into a number of time periods. There was the time of the creation, which on day 3 there may have been geological work when the dry land appeared from the waters. That's still uncertain because creation was one giant miracle. Then we had a pre-flood period for approximately 1,700 years. That's probably, you had pretty low geological action. Then you had the Genesis flood for 371 days. And then we had a post-flood period of which the Ice Age occurred. And then we can, when we look at the account of the flood in Scripture, we can formulate a biblical geological model just on the flood. From the Bible, the flood occurs by some catastrophic, huge mechanism all worldwide. The water rises. Then it comes to a peak approximately day 150. It appears that water rose fast for the first 40 days, and that's what you'd expect in the mechanism being so catastrophic. You'd expect most of the flooding soon, and then the Bible talks about it prevailing up to day 150, so that kind of implies a slow rise. And then the arc rounds on the mountains of Ararat, and that would indicate that's probably near the peak of the flood. And then at day 150 to day 371, a total of 221 days, the flood is draining off the continents. As the continents rise up out of the floodwaters and the mountains rise and the valleys sink down and the ocean basins sink. So we can divide up this flood into a flooding stage, which would be your first 150 days where the water rises to a peak, and then a receding or retreating phase stage, in which the water is running off for 221 days. So there's two stages of the flood, the flooding stage and the retreating stage. Then we can divide those up into phases, of which there's 2 phases for the flooding stage and 2 phases for the retreating stage, and 1 phase in the middle at the peak. The first phase would be the first 40 days when you had huge catastrophism, huge big currents, a lot of turbulence, because the mechanism is so powerful. And they had 40 days and 40 nights of rain that probably was the cause. 40 days is probably telling us that it was waning, the mechanisms were slowing down, so all the turbulence was waning, and so from day 40 to day 150 would be a second phase, and then around day 150 at the peak would be another phase. And then during the retreating stage of the flood, water's covering the earth at day 150, the whole earth. The water's starting to recede. When it's doing that, the water's moving across the earth in wide currents and probably fairly deep, probably several miles at least. We'd call this the sheet flow phase because the water currents, if you looked at them down current, they would be very wide, maybe 1,000 miles wide and 2 miles deep. We can bring that to smaller scale, they'd have the shape of a sheet. Very thin and wide, so we call it sheet flow. But as more mountains are exposed, either they rose up or the water's decreased, and plateaus were exposed also, the water's forced to channelize around these. Then we switch from more of a sheet flow to more of a narrow current, and we'll call this the channelized flow phase. Now each of these 2 phases during the retreating stage of the flood erode the continents in a different style. Sheet flow generally will erode huge areas and cause planation surfaces and transport resistant rocks from that erosion process long distances. During a more channelized phase, different features are formed, and these features are superimposed on the features already produced during the sheet flow phase. And these would be canyons, valleys. After you've already eroded a lot of material, you form the canyons and valleys during the channelized flow phase. And when you're forming canyons and valleys, and in some valleys, the flow was going so fast you form planation surfaces along the edge called pediments. Also, where water was going perpendicular to ridges and channelizing, it cut water gaps all the way down to where water's running through the mountains or the plateau or ridge, and you cut wind gaps that aren't cut far enough down. And also, as the material eroded during the sheet flow phase in wide currents, gets deposited along the continental margin. It's just taken clear off the continent, and it forms the thick sediments of the continental margin, of which the profile is called a continental shelf at the top, and then you have a drop-off called the continental slope. And off of some continents, you have a gradual descent into the deep sea, and that's called the continental rise. And those sediments, of which sometimes they're 15 kilometers, 20 kilometers thick off the east coast of the US, for instance, 25 kilometers thick in the Gulf of Mexico, just thick sediments from the runoff of the continents form the continental margin sediments that are, it's like a bathtub ring all around the continents. This bathtub ring extends way out. The continental shelf can go out hundreds of miles. If you can drain all the ocean water and see the geomorphic features of the surface, this would be the most conspicuous geomorphic feature on the Earth, is the continental margin. That was deposited during the sheet flow phase. But during the channelized flow phase, the current sped up and channelized and cut submarine canyons. We're in the lower canyon of the Clark's Fork River Valley before it enters the Bighorn Basin. This is a great location to talk about tectonics. That's vertical changes in the crust of the earth during the recessional stage of the flood. Now behind me, you see the edge of the Beartooth Mountains. And actually it's a part of the Beartooth Mountains, that dark area there, sloping down with a flat surface. And on top of that are Paleozoic, mostly limestones piled on top of it. Well, as the Beartooth Mountains uplifted and this limestone area uplifted, it bent the rocks on top of it to a vertical angle and eroded. This material that used to be on the Beartooth Mountains way up there got washed off, and it moved east and piled up into a huge, what I call flood fan of limestone blocks and rocks cemented together. This fan probably had an angle like that to the Beartooth, and as the Beartooth continued to uplift, it became an angle like this, about 30 degrees dipping down towards the east. And then this area was eroded somehow, leaving erosional remnants of that flood fan out to the east about 2 miles. As a Bighorn basin sank and filled up with sediments during the recessional stage of the flood and the Beartooth Mountains uplifted, there was a fault here called the Beartooth Fault, where the Beartooth Mountains rose, the granite in the Bighorn Basin sank. You find the granite 10,000 feet below sea level. Well, up on the Beartooth, it's 13,000 feet above sea level, indicating a change of 23,000 feet at the Beartooth Fault. You can see in the background these strongly tilted rocks. In the Bighorn Mountains to the east, we have a similar uplift and tilted rock. You generally don't bend rock unless it's really deep and under pressure and heat without breaking it. So this bending to vertical strata, tilted from about 30 degrees to vertical here, probably implies that the sediments were not quite solidified, or they were partially soft. It also implies another thing. If this uplift was slow over millions of years, these vertical features would all erode in that time, and you wouldn't have features like this. And same with in the Bighorn Mountains, where you actually have overturned strata like this as the Bighorns came up. You wouldn't have that if this was slow uplift over millions of years, because it would erode. Erosion's pretty fast on a million-year time scale. This implies rapid uplift, consistent with what we expect during the recessional stage of the flood, when the mountains rose and the valleys sank down. And this theme of the mountains rising, the valleys sank down, is a theme all over the earth, even on the ocean bottoms. Most of the ocean bottom consists of abyssal hills, which are faulted up hills and folded down next to it. Before we discuss the sheet flow phase, we have to talk about what causes the water to drain off the continents and about the erosion of the continents. Psalm 104:8 tells us that the mountains rose and the valleys sank down when the floodwaters drained. And this was referring to the flood, because verse 6 says that God covered the land, including the mountains, with the water. The only other time the earth was flooded was on day 2 and 3, and on day 3 the dry land appears out of the water, and that's an uncovering. So it's obvious that from verse 6 that it's referring to the flood. And verse 9 reinforces this, where God set a boundary that the water that's in the ocean now will not come back up over the earth. When you have mountains rising, valleys sinking down in a flood, the water is going to rush off into the valleys and off the mountains. And also this occurs on a large scale, where the continents are coming up out of the floodwaters and the water's rushing off at high speeds. We have a lot of evidence of the ocean basin sinking in the form of guyots, which are formed near sea level. These guyots are flat-topped seamounts, and a seamount is a volcano, an underwater volcano. They're planed at sea level, near sea level, and now they're 5,000 feet below sea level, indicating that the ocean basins have sunk. And the margin along the continent is sunk. We have evidence of sinking of 14 miles in spots along the east coast, it was estimated, between the top of the Appalachians and some of the big cracks that are filled with sedimentary rocks in the coastal plain and on the continental shelf off the east coast. So you had a lot of upward vertical tectonics, and this is what drains the floodwaters off. As it's draining, it's going to erode the land during the retreating stage, both during the sheet flow and the channelized flow. The erosion will be different. When we look at the continents, we can tell that it's been greatly eroded in bulk. For instance, the Colorado Plateau, it was estimated that we've had anywhere from 8,000 to 15,000 feet of erosion over the whole Colorado Plateau. Other erosional numbers are in the literature. For instance, in southern England, it's been estimated a mile or so of erosion. In the Canadian Rockies and the foothills, about another mile. Over the Flinders Range of Australia, it's been estimated about 20,000 feet. In the Appalachians, it's been estimated about 20,000 feet of erosion. Now, I ran a calculation to verify some of this erosion, and there's two ways you estimate the erosion. There's lots of coal in the rocks. Coal needs sediments above it, and it needs heat and pressure. So from the coal rank, which determines how hot it was, you can figure out roughly how much overburden. And based on coal rank, you can estimate about 20,000 feet of erosion in the Appalachian area. Another calculation is to check the sediments off the east coast where the floodwaters were eroding the mountains, taking those sediments to the east and deposited them in the continental shelf slope and rise. From that estimate, and by the way, we have those estimates based on seismic reflection profiles. We can find the igneous metamorphic basement and the sedimentary rocks have been estimated. And again, it comes out close to 20,000 feet of erosion for the Appalachians. And for the Colorado Plateau, there's a calculation that you can do based on north of the Grand Canyon. There's the Grand Staircase where the sedimentary rocks are tilted down to the north about 3 degrees. And there's a series of cliffs and steps, cliffs and steps. In other words, there's 5 of them of sedimentary rocks and a 6th at the very top that's volcanic. Based on that, if you extrapolate those sediments up over Grand Canyon area, you can show that around 10,000 feet of sedimentary rocks were taken off as a sheet, forming a planation surface over that whole area. That would occur during the sheet flow phase of the retreating stage of the flood. Another calculation on the Colorado Plateau I made near the Book and Roan Cliffs near Price, Utah. Again, the sediments, they tilt about 6 to 8 degrees to the north. And based on trigonometry, I estimated the amount of erosion over the San Rafael swell to the south. And I got up to 17,000 feet of erosion over the San Rafael swell. So these figures are huge erosion over the continents, are based on sound geomorphological science. Eroded domes where the center's eroded and the sedimentary rocks are tilted. You just have to extrapolate them up over the dome, and then you can figure out how much erosion. That's a way that's used, and that's where we determine that there's thousands, sometimes 10,000 or 20,000 feet of erosion over places of the continents. Sometimes we have erosional remnants like Devil's Tower that sticks up, but usually erosional remnants are just very minimum estimates because sometimes it's a sedimentary mesa where the rocks are hard at the top. So to harden rock, they have to be buried a fair amount. So they're always minimums. Based on erosional remnants, you can get minimums in a lot of places of 1,000 or 2,000 feet just based on the top of the erosional remnant. But then if you add the sediments that would be needed to harden a rock that's now on the top of the mesa, you'd have to add another 1,000 feet or more. These are some of the ways we figure out that the continents were greatly eroded. These erosional products are not found nearby as if it was eroded by uniformitarian time over millions of years. They're gone. They're taken totally off the continents. This is what we expect in the flood. Not only the huge erosion of thousands of feet, but to be totally taken off the continent, and now it's in the continental shelf. The continents have been greatly eroded. And during this erosion, of course, it forms planation surfaces and spreads the resistant rocks long distances. That's why you can go to a lot of places and go down through a thin soil and find bare rock. I mean, if we had millions of years of erosion and soil formation, we should see dozens of feet of thickness of pulverized rocks, soils, or even hundreds of feet. There's exceptions because we have a lot of post-flood landsliding and other features that would form thicker debris piles or rock piles and soils. This erosion we know happened rapidly. And the best example on this is Devil's Tower. Now, Devil's Tower in northeast Wyoming is approximately 1,200 feet tall and 1,000 feet wide. It goes straight up. It's very likely the throat of a volcano. The throats of volcanoes, or even if it's some other mechanism, still has to form under sedimentary rocks. So the sedimentary rocks in northeast Wyoming, in that whole area there, had to be at least to the top of Devil's Tower, and very likely much deeper, maybe 6,000 feet above that. In fact, the Uniformitarian geologists believe it was 6,000 feet deep there. But as you eroded all this sedimentary rocks from the top of Devil's Tower, 1,200 feet down, Devil's Tower was hardly eroded at all. The width of it's still the same, and supposedly this happened over millions of years. How can you erode a horizontal surface over thousands of square miles, and yet Devil's Tower with vertical walls is hardly touched at all? Well, that makes no sense at all, because vertical faces erode faster than horizontal surfaces by far, because we have a lot of rock fall. Not only that, Devil's Tower has a lot of cracks in it called joints. In that area, you get a lot of water in there that would freeze and thaw, and that would tend to want to expand and knock that Devil's Tower into a pile of blocks. In fact, I don't think Devil's Tower can exist more than 10,000 years old. But the fact that it's still there, well, all the plain strata got eroded thousands of feet down, indicates you had to do it rapidly, because we know that if you eroded this field right now by a flash flood, the erosion leaves erosional remnants. It's typical of floods to leave erosional remnants. And so for some reason, Devil's Tower was a little harder probably, and therefore the flood could not erode it out, and it left it hanging as a vertical tower 1,200 feet tall. Well, we're on the western edge of the Bighorn Basin here, just east of Dead Indian Pass. The Bighorn Basin is about 70 miles east-west and about 120 miles north-south, and it's filled with sedimentary rock. In the northern Bighorn Basin here, it's filled with about 15,000 feet of sedimentary rock. In the southern Bighorn Basin, it's about 25,000 feet. And further out is the Bighorn Mountains, which rise up to 13,000 feet. Just in front of us is Hart Mountain, which is one of those limestone blocks that broke off from a huge limestone depositional area east of Yellowstone Park and slid, moving over 100 miles an hour to the southeast. And this is one of the blocks that slid out into the western Bighorn Basin. It's not the furthest block that slid. The McCullough Beaks, way out there that you can't see, is the furthest block of limestone that slid. One of the significant things about Hart Mountains is that it slid on top of the valley fill sediments of the Bighorn Basin. And when you look at it, the base of Hart Mountain stands about 1,500 feet, maybe up to 2,000 feet above the bottom of the valley. So after all this material collected in the valley, the top was eroded about approximately 2,000 feet or more, and I believe that happened during the channelized phase of the flood. The basin itself likely filled up early in the retreating stage during the sheet flow phase, when the Yellowstone Park area and the Beartooth Mountains were rising. The basin was sinking and sediments just filled it up, and it was deep water here, I'm sure of it, and sediments from the tops of the mountains and from way up current were deposited in this basin early, and then the slide happened, and then the flood flow channelized going from south to north. It eroded up to 2,000 feet below the base of Hart Mountain, indicating the amount of erosion that occurred in this valley late in the flood. And this is probably the amount of erosion that occurred in other valleys and basins in southwest Montana and Wyoming. Wyoming's mostly a state with mountains that have risen and basins that have sunk and filled with sedimentary rocks. In fact, If the granite crust was level midway in the flood, about day 150, and parts of the granite went up and parts went down, the total differential vertical tectonics is up to 45,000 feet, based on the height of the Wind River Mountains, the highest mountains in Wyoming, which are up to 14,000 feet, and the deepest part of the granite, which is in the Hanna Basin in south central Wyoming, which is 31,000 feet below sea level, filled in with sediments up to about 7,000 feet above sea level. So there's 38,000 feet of sediments in the Hanna Basin. In fact, all these basins in Wyoming are filled with thousands, tens of thousands of feet of sediments. And then the top 1,000 or so was eroded off during the channelized phase of the flood. Well, here we are in the Madison Valley, about 20 miles south of Ennis. And before us, we have a real very unique mountain. It's called the Sphinx. Next to it's called the Helmet. In between there's a saddle. What this mountain is a pile of conglomerate. Most of the rocks are limestone cemented together, and there's 3,000 feet thick. And there's also cross beds indicating currents that deposited catastrophically. But it's the only mountain like this in the Madison Range. But there's also about a dozen other mountains throughout southwest Montana that form some of the highest peaks in the ranges of southwest Montana that are like it. It's reddish because there's a lot of iron oxide within the limestone conglomerate. Also, we find the same conglomerate down in the valleys. So how do we explain this? I think this gives us a big clue on what happened late in the flood, because you didn't really put a fence around where the Sphinx is right now and then just dump 3,000 feet of conglomerate somehow. No, it had to be laterally extensive. And when you connect the Sphinx with other mountains in here, it looks like we had 3,000 to 5,000 feet of limestone conglomerate that was maybe 60 miles wide north-south and maybe 30 miles east-west. And it's the same type of limestone we find in the mountaintops of these mountains. But it couldn't have come from there because it's sitting on top. So where did it come from? Here's what I think happened. I think the limestone came from the west. And to the west of us is a granite outcrop called the Idaho batholith over a wide area. And this limestone probably was continuous into Idaho. And the granite uplifted in the floodwaters, and the floodwaters, moving at high speeds, tore up the limestone and moved it east and formed a huge flood fan, 3,000 to 5,000 feet thick, up to 5,000, because one of these limestone mountains is 5,000 feet thick of a conglomerate. And then this area, the mountains uplifted and the valley sank down and just tore this fan up. 95% of it eroded out and left about 5%, of which some came up with the mountains and formed these isolated peaks of a limestone conglomerate. What is the big picture that went on here? Well, it was late in the flood when the mountains were rising and the valley sinking down, and the floodwaters were eroding the tops of the mountains that were rising, starting from the west and moving east, forming this fan. Powerful evidence of the deposition from this erosion, and then the tearing it apart. Just tremendous tectonics. Probably 10, 20,000 feet of tectonics occurred here, of mountains going up and valleys sinking. So this is powerful evidence of what happened in the retreating stage of the flood, when the mountains and the continents were rising up out of the floodwaters, and the valleys, like this valley here, and the ocean basins were sinking, and the water was running off at high speed, eroding the continents, in some cases eroding and spreading the gravel just to the east of where it was eroded from, forming this fan. And then it's interesting that there's lots of quartzite conglomerate and gravel all through this area. Some of it's high up in the mountains and some of it's down in the valleys. But the quartzite is not mixed in with the limestone except very locally, and the limestone conglomerate came first. It's kind of interesting that the belt formation probably had limestone on it, and once it got eroded and spread, then the quartzite eroded on top of it and was generally separated from the limestone. And if any limestone was mixed in with the quartzites coming from the west, the powerful turbulence probably would pulverize it, so you generally have just limestone gravels and conglomerates separate from the quartzite gravels. During the erosion of the continents, when we examine the character of the erosion, we can determine that, first of all, that it was rapid and recent. For instance, along southern Africa for about 2,000 miles, the edge of it is ringed by an escarpment. Escarpment is a high cliff. The escarpment is sometimes vertical, sometimes sloped like this. It looks like it's flat on the top, like a tableland as they call it, but it's really a planation surface where it's been planed flat during the sheet flow phase of the flood. And then you got to have the escarpment, and then you have a coastal plain. Now there's debate among uniformitarians on the origin of these escarpments. In fact, they have serious trouble explaining them, but it looks like the sediments were closer to the coast, the sedimentary rocks mostly. There's sometimes igneous rocks in them, and that the escarpment backed up from the coast, sometimes maybe 60 miles or more. It appears that the water from the flood was flowing off as a sheet perpendicular off the coast towards the ocean, and it was forming like a huge waterfall, or in this case it'd be kind of a little ripple because we're talking about deep water. And so it's eroding the escarpment back. And then the coastal plain, it shows some dissected planation surface, but the planation on the top above the escarpment is still generally flat in many of these escarpments, especially in South Africa. Now in Southeast Africa is the most spectacular one. It's called the Drakensberg, where it's about 10,000 feet high is the escarpment. You find these escarpments along other coasts. They're called, we'll call them coastal escarpments. And they're erosional escarpments, not faulted. You find them in eastern Brazil, you find them in western India, and you find them in eastern Australia, almost the width of Australia, about 1,500 miles long. In Australia, it's about 3,000 foot high escarpment. Some places it's totally eroded, and so in a few little places it's eroded out. The fact that you still have cliffs and steep slopes indicates that these escarpments were eroded not very long ago, because vertical faces and steep slope erode a lot faster than horizontal surfaces. And also, uniformitarians have the bind where these escarpments are fairly young. They're in the Cenozoic era, probably around 50 million to 30 million years ago in their time scale. So they're recent. In fact, the erosion is too fast for their time scale, so they're kind of searching around for other mechanisms. But during the flood, they can form rapidly, and the fact that there's still vertical cliffs and steep slopes indicates that these escarpments were formed not that long ago. Another indication of rapid erosion is the leaving of erosional remnants. There's thousands of them across the earth. Sometimes there's sedimentary remnants like a mesa with vertical cliffs around it, maybe 1,000 feet tall. You have some of these in the middle of the Powder River Basin of northeast Wyoming called the Pumpkin Buttes, indicating 1,000 feet of sediments were over that area and were eroded off. And since there are hard rocks at the top of the Pumpkin Buttes, you can add probably another 1,000 feet, indicating 2,000 feet over the whole Powder River Basin was eroded off at one time. Well, here we are, just a little west of Graybull, Wyoming, in the northeast Bighorn Basin, and we're standing on a planation surface, a gravel cap planation surface, many of which are well-rounded quartzites by water action, but there's a number of local lithologies in this gravel too. Behind me, you see the planation surface on the other side of the highway. It used to be continuous in here until it was eroded out to where the highway is down below us. Some planation surfaces are cut on horizontal sedimentary rocks where it's eroded it down a lot, but it's still on horizontal, and sometimes it's hard to tell that this is a planation surface. And a great example is around the Grand Canyon area, where you've taken off anywhere from 6,000 to 10,000 feet of sedimentary rocks in the whole Grand Canyon area and left generally a flat surface. That's why the top of the Grand Canyon is so even. It's a planation surface. But the really nice planation surfaces, the ones you can really tell, is when the beds tilt at an angle. Like this one we have here, where it's tilted down to 30 to 50 degrees to the west, and yet it's been sheared off at the same angle. The tilted sedimentary rocks are on valley fill, the Bighorn Basin, and valley fill is usually a combination of hard and soft rocks. The water that created this planation surface planed it off at both hard and soft rocks the same, and left rounded rocks, of which many of them are quartzites from 300 or 350 miles away in central Idaho. Well, here we are in the Beartooth Mountains at Rock Creek Vista Point at about 9,200 feet on the way up to the top of the Beartooth on the Red Lodge Cook City Highway. What you see before us, besides Rock Creek, you see the tops of the Beartooth. The Beartooth Mountains represents one huge planation surface, planed in granite and gneiss. And it's been uplifted and faulted to different elevations. The elevation you see here is about 10,000, 11,000 feet. The top peaks here are the highest peaks in Montana, like Granite Peak at over 13,000 feet. And when you see those, they're planed off flat. Well, the planation surface has been considerably roughened by erosion, but you can generally see it if you just look at the ridges around and some of the parts that have been folded up that are still flat top. And not only has it been roughened, but it's been dissected. Probably when it came up, it cracked, and water during the channelized flow phase of the flood took advantage of those cracks and widened them, like we see in Rock Creek here. Now, this planation surface, it could have formed at 2 times during the Genesis flood. It could have formed early in the flood as an exhumed surface. The exhumed surface is one that's formed, flattened, and then sediments pile on top of it, and then it's re-eroded or exhumed. As it uplifted, there's evidence that the top of this granite was eroded because we find erosional remnants of the limestones and other rocks that were capping this at one time. Or if it's an exhumed surface, it could have been made early in the flood when there was a huge amount of turbulence that caused fast currents to just plane down the upper crust, this is the upper crust of the continents right here. It could have planed it down. But there's evidence that this could have happened late in the flood during runoff. The reason is because you have a lot of plain mountains in the area. The tops of the Wind River Mountains are planed flat. Also, the southern Absaroka Mountains have been planed flat and dissected, and the Absaroka Mountains formed late in the flood. So planing did happen late in the flood. And when the Wind River Mountains rose, it eroded the sedimentary rocks off the top of it, and it tilted the sedimentary rocks along the edge. And some of those sedimentary rocks that were tilted were planed flat. And that would happen late in the flood. So at this point, I have not made up my mind whether this is an exhumed planation surface early in the flood or late in the flood as the floodwaters were running off the continents. Well, planation surfaces are found on all the continents, even in Antarctica, because some of the mountains that stick up out of Antarctica are planed flat. Often planation surfaces are at the tops of mountains. In fact, 2 secular geomorphologists wrote a book on the origin of mountains. They believed that planation surfaces were very extensive at one time, because at one time the earth was pretty flat, and this was probably midway during the flood. And then suddenly uplift occurred and breaking up of this planation surface mountains formed and erosion occurred because this is mostly underwater, and often the planation surface was totally destroyed, so you have pretty sharp mountains. Other times it wasn't. So the planation surface is still left on the tops of the mountains. And I go along with this because there's a lot of planation surfaces even in the Rockies. You still see some in the tops of the Colorado mountains. You see the Wind River Mountains, the Uinta Mountains are planed, the Absaroka Mountains, and here the Beartooth Mountains, and many other mountain ranges of the Earth have been planed. So I go along with Ollier and Payne's hypothesis that we had a huge planation surface at one time that uplifted, faulted, and eroded. And this goes along with another geomorphologist from the University of Natal in South Africa, Lester King, a renowned geomorphologist. In fact, he was a world traveler. He documented these planation surfaces on all continents. And he said they were once much more extensive, and they've since been eroded to smaller remnants. By smaller remnants, I mean they might be 1,000 square miles or even some places 10,000. In Africa, there are hundreds of thousands of square miles in extent, like the Serengeti is a flat planation surface. The sedimentary rocks and metamorphic rock, igneous rocks below it are warped like this. And if you'd extend those up above the surface, they'd be like this, and they've been planed flat by some powerful current over a huge area, indicating the width of the current. These planation surfaces once were much more extensive, but been eroded to smaller remnants since then. There's evidence that practically all the mountain ranges in the western United States had thick sedimentary rocks on them before they uplifted. Behind us is Beartooth Butte on the top of the Beartooth Mountains and in front of Beartooth Lake. It's about 1,500 feet erosional remnant, about the only one on top of the Beartooths of the rocks that were on top of this planation surface. This could be evidence that this planation surface was exhumed. You had thick sediments on it and then they washed off. Beartooth Butte is in a pocket and it's pretty rough in here, so it's possible that the planation surface formed late in the flood during flood runoff and left Beartooth Butte in a pocket as an erosional remnant of the material that was washed off. Now the material that was washed off occurred when the mountains were coming up and the valley sinking late in the flood to drain the floodwaters. And much of this material that eroded off ended up as valley fill in the surrounding valleys. And then the top of this valley fill was later eroded when the floodwaters became more channelized going down the valley. Speaking of exhumed surfaces, these are planation surfaces formed early in the flood by turbulent, fast currents. And there's evidence over the western United States, wherever you see the upper crust, which is mostly granite and other metamorphic rocks. When you see this, it's generally a flat surface. That's why it's possible that the tops of the Beartooths, which are plain granite, are an exhumed surface, and same with a lot of other mountain tops. Some may be, and some may be from late in the flood. I have not made up my mind. There's evidence both ways. But you see this exhumed surface with the sediment still on top of it in Grand Canyon. It is called the Great Unconformity in the Great Grand Canyon, where it's a general planation surface on top of the granites and metamorphic rocks. And on top of it, you have about 4,000, 5,000 feet of horizontal sedimentary rocks on top of it. So it appears that the Great Unconformity extends over much of the western United States, and we see it sometimes where the mountains have been raised up. We are at Carter, Montana. Now, this area here between Great Falls and Fort Benton is where a man named William Morris Davis developed his idea of the cycle of erosion, or the geographic cycle. It's an evolutionary uniformitarian theory started in the 1800s. William Morris Davis was a professor of geology at Harvard University. He came out here in the summer to do the surveying work for the railroad. In this location around in here, he developed the cycle of erosion, which became a very popular idea on how to form landscapes. He noticed the Highwood Mountains way off in the background that are rather hazy today, and they're generally igneous rocks, and sedimentary rocks are a lot thicker in this area, so he realized this area was tremendously eroded, and eroded down to a generally flat surface, as you see out there, and another flat surface, the Fairfield Bench, to the west. He developed in the late 1800s a cycle of erosion that said that landscapes go through an evolutionary process. He was a strong evolutionist. So they start off with generally rolling or flat, and they uplift, and then with time, over millions of years, they dissect. When they first uplift, that's a youth stage, and when they dissect and they wear down, they're more the mature stage, and finally they wear way down to a rolling surface called a peneplain. This is many tens of millions of years for this, and he said that the land surface went through this cycle. Then it repeats itself, it uplifts, and the cycle starts all over again. This is called the cycle of erosion. It was extremely popular and well taught from the late 1800s to about 1950 or 1960, until they realized it was mainly a deduction with little testing of evidence, and so it's been rejected for 50 years. It is interesting that William Morris Davis, who's one of the fathers of geomorphology, the study of the surface of the earth, before he developed a cycle of erosion, believed and stated that once you threw out the Genesis flood, we should be able to explain the scenery around us within the next 100 years. It should be easy with uniformitarianism and slow erosion over millions of years. But he's so wrong, because his idea has been thrown out since the 1960s because they can't find evidence to really support it. It sounds like a good idea, but they can't find it. So what they've done, instead of studying landforms and planation surfaces, they decided we're going to study the processes affecting these surfaces or landforms, which is called process geomorphology. So for 50 years they've been studying river erosion, landsliding, things like this, that they should have started with in the 1800s before they even developed these broad-scale theories on how landscapes form by the cycle of erosion. By throwing out the flood, they've gotten nowhere. But when we bring back the flood into Earth history, we can explain these landforms, these planation surfaces, flat surfaces that are eroded down, leaving rounded rocks on the top. We can explain them by the runoff of the floodwaters. So bringing back the Genesis flood into Earth history, we can explain the surface features of the Earth. Well, here we are at 9,500 feet at the top of the gravelly mountains in southwest Montana. This is one of the 4 locations where there's known quartzite rocks surrounded by water action that have been spread from central Idaho, northern Idaho, and extreme northwest Montana. This location was considered an ancient Ice Age deposit because the quartzite was a lot of times in finer grained sediments around it, because as it moved from its source, which is at about 100 miles to the west, southwest, and central Idaho, it picked up a lot of other rocks and pulverized them. So when it was deposited here on what is now the top of the gravelly mountains, it was floating in these finer grained sediments. So they thought it was an Ice Age feature from the Eocene 50 million years ago. But the Eocene's way too warm, they had to throw it out, so it ended up being, they claim, from a landslide deposit. And I believe that's probably the last movement of this material was from a landslide. A lot of the material you can see up in there, that's the landslide deposit, and that is full of quartzite rocks, some of them very large. The larger the rock, the more the current you need to move them. Here is quartzite. This is one of the largest ones in here. It's over 2 feet in diameter, and it also has percussion marks, semicircular cracks on it. Also, it has an extra feature I've only seen one other time in a quartzite, and that was on top of the Wallowa Mountains. And it's chatter marks, which are cracks made in a line like this from probably bouncing on another rock in the water. So we have quartzites on tops of 4 mountain ranges, and this is one. What are the other 3? The other 3 are the Wallowa Mountains in northeast Oregon. At numerous locations on the very tops of those mountains, you have abundant quartzite. Some of them are about this big, like this. And they're also on top of the Blue Mountains, like Gold Hill north of Burns, and it's called Gold Hill because right in the quartzite gravel, you have gold in there, and people have dug into the quartzites for gold in the finer particles. North of Burns in the Blue Mountains is about 250 miles from its source in the central Idaho, but to the west. That indicates some of the power of the currents that move this when there's gold in the finer material. And that's not the only place in the top of the Blue Mountains. You find gold in other quartzite locations. The 4th location we find quartzite is on top of the northern Teton Mountains. There's a few flat top mountains in the northern Tetons. One of them is Mount Moran, about 12,000 feet. I'm not sure there's any quartzite on the top of that, but there's a mountain just to the northwest called Red Mountain, 10,200 feet. And on top of that, there's rounded quartzites about this big with percussion marks on them. So those are the 4 locations on mountaintops we find them in this area. We find them at numerous other locations besides on mountaintops. We find them in valleys, we find them on plateaus out in the plains. And of course, we find them 800 miles from their source in central Idaho to the northeast and east. We find them clear to the Pacific Ocean. We find them a lot of times on the highest terrain, not only mountaintops, but the tops of lava ridges around Yakima up over 4,000 feet above sea level. We find them in Puget Sound area mixed with the glacial debris. In other words, what are these quartzites rounded by water over an extensive area indicating flow of water both east and west of the Rocky Mountains? What is it doing at the top of a mountain? I believe that the quartzites found on these mountain ranges tell us a lot about the tectonics late in the flood. See, the quartzites were spread late in the flood, first by sheet flow and then more channelized flow. And this tells us that they were spread long distances, probably on a generally level surface to start with, maybe a little bit after day 150 to day 200, for instance. And then we had the mountains rising and the valleys sinking down, as Psalm 104:8 says, to drain the floodwaters. The quartzites that spread over this whole area, and they're extensive by the trillions from here into North Dakota, Saskatchewan, Manitoba. I believe that quartzites were deposited and they came up. They didn't skip over mountains. We're about 4 or 5 mountain ranges from their source. They flowed generally on a level surface and the mountains carried them up. That's the only way I can explain it. I believe that's a very reasonable explanation. This is just one quartzite location in the Gravelly Mountains. There's a number of other locations on the tops of these mountains. They don't call it the Gravelly Mountains for no reason at all. One of the reasons is you have nice rounded quartzites. This one right here probably weighs 400 or 500 pounds. Can you imagine moving that from central Idaho? We're talking about currents well over 50 miles an hour to move something like this, especially in turbulent flow, to cause rocks to bang against each other to form the percussion marks. Another feature we have in this area is that, the mountains came up to bring these up, but sometimes the valleys dropped, and sometimes they dropped really deep. And sometimes the quartzites came and just filled those paleo valleys up, or cracks. One location just south of the Montana border in Idaho, there's one large location approximately 20 miles east-west and about 10 miles north-south that fills up a crack 15,000 feet deep of rounded rocks like this. Some of them are really huge. I've been up to the top of it. They filled it up with rounded rocks. Can you imagine that? In fact, the pressure was so great on these rounded rocks that quartzite against quartzite caused pressure solution marks in some of the quartzites. So once it deposited that 15,000, actually it was more, because we know the top was eroded out. It's probably 20,000 feet, and then a lot of that came up too and was eroded off. And some of those rocks with pressure solution marks still on them were transported well to the east, and some are on top of the Teton Mountains with pressure solution marks showing the pressure that it was under in that big paleo valley. There's a second big deep paleo valley, and this one's more 50 miles north-south and about 10 to 20 miles east-west, and it's just east and northeast of Jackson, Wyoming. It starts in south-central Yellowstone Park. It forms some of the mountaintops, and it goes down east of Jackson. And it forms some of the high mountains in there. One's called Gravelly Mountains, and you can see 1,000 feet cliff of rounded rocks like this piled up and cemented together. And that location is 11,000 feet deep. And according to David Love, state geologist from Wyoming for many years, he claims that 80% of it's been eroded. In other words, you had much more of it there, and then it was eroded and sent east. And there's lots of it to the east of Jackson Hole in the valleys further east, like the Bighorn Basin, the Southwest Powder River Basin, the Wind River Basin. A lot of them piled up and then were re-eroded. Just think of just the force to move all these rocks and pile them so thick that now they form some of the mountain peaks northeast of Jackson. Here we are out in the middle of the west central Bighorn Basin in the middle of nowhere. And lo and behold, here we find quartzite outcrop of a high-grade quartzite. This is just a small little erosional remnant of a much larger area of quartzites that goes north-south about 25 miles in here. We're about 30 or 40 miles from the Beartooth Mountains and the Owl Creek range to the southwest. Quartzite does not outcrop in the state of Wyoming. The nearest source to the west, which is upcurrent in a flood, is central Idaho, approximately 300 miles from this location. And besides that, there's about 5 or more mountain ranges between here and its source in central Idaho. So how did it get here? Did it skip over the mountains that were here? Oh no, it was spread long distance before the mountains uplifted. Then the mountains uplifted, carrying some quartzites to the tops of the mountains, and some remained in the valleys, like this one in this big valley, so big it's called a basin. It's 70 miles east-west, 120 miles north-south. Now when you examine the rocks here, you find a number of interesting features. These quartzites have the usual percussion marks on them, and also they have pressure solution marks. Now pressure solution marks are these white marks on this quartzite cobble right here. And they're formed to the west of us in those areas where thick quartzites accumulated in some crack. The nearest source of thick quartzites that piled up very deep is east and northeast of Jackson Hole. And when they pile up, it's rock against rock, and where they touch each other, the pressure is so hard that it kind of recrystallizes the hard quartzite right there because of the thick weight of rounded rocks on top of it. And that area of rounded rocks east and northeast of Jackson is right now up to 11,000 feet thick. But according to David Love, a past state geologist from Wyoming, he said 80% of it is eroded. So what happens, it piled up even thicker than that. And the top got eroded, and we're east of that area, and so some of the rocks with pressure solution marks have made it this far. Not only do they have pressure solution marks, the weight of the quartzites also fractured a lot of the quartzites. For instance, this little one right here has a fracture through it, and a lot of times I can tap them with a hammer and they'll shatter. I don't know if this one, that fracture looks still pretty strong, but I'll try it. There you go, a hard rock. Normally a rock that size, I'd have to hit it with all my might to break it open. But this, because there's a fracture through it, because of all the weight of rounded rocks above it, it's fractured, and so it was easy to break open. In fact, there's some weathering in the fracture. Another feature we find is, of course, percussion marks from this boulder. Now this boulder was probably this long, and there was a fracture through it, and so it broke. But it's loaded with percussion marks, dozens of them, if not hundreds of them, semicircular cracks on one of the hardest rocks in the world. And it's pretty heavy and dense because all the pores of the sandstone have been filled in, recrystallized during the metamorphic process forming the quartzite. And then during the transport process, the extreme turbulence, I believe, caused these percussion marks on this rock. These quartzites are not the furthest east of the quartzite locations found. Well-rounded quartzites by water action are also found in the eastern Bighorn Basin, another 30 miles that way. Also From the literature, I've visited many of these quartzite locations, by the way, but from the literature, there's a quartzite location in the southwest Powder River Basin on the other side of the Bighorn Mountains. So that's another 80 miles away or so. So the longest distance transport east from central Idaho is approximately 400 miles for this quartzite gravel. The continental shelf and slope is a major geomorphological features of the Earth's surface. You don't see it because it's all underwater. It's a very slow decrease of the slope out into the deep sea. It's very shallow and the slope decreases. The average is about 50 miles wide, but some continental shelves are so wide they're 300 miles wide, like the Bering Sea shelf, the Arctic coastal shelf, the South China Sea continental shelf, and then at the edge of the continental shelf, about 400 feet of water, then you suddenly have a drop-off called the continental slope. These sediments in the continental shelf and slope indicate that the currents came from off the continents, formed this shelf around all the continents of the world during the sheet flow phase. And the sediments are quite deep in areas. Off the east coast of the United States, the sediments that accumulated there are 15 to 20 kilometers deep in spots. And in the Gulf of Mexico, that continental shelf and slope are about 25 kilometers deep. A kilometer is about 6/10 of a mile. There's 4 main landforms all over the Earth that occurred during the channelized flow phase of the flood. Of course, valleys were cut rapidly, but I'm not including those. The first landform is vertically walled canyons. We know canyons can form by flood waters because in the Lake Missoula flood, flowing through eastern Washington at up to 60 miles an hour, it formed vertical walled canyons in flat bottom valleys called coulees. So we know floods cause vertical walled canyons. The 3 other features are water and wind gaps, pediments, and submarine canyons out on the continental shelf perpendicular to the shoreline. At this point, we're going to talk about pediments. In Montana, we have hundreds of pediments, various sizes and scales. Some are up to 100 square miles. Right now we're sitting on part of an eroded part of the pediment, which you can see out in the horizon there, across this little valley. You can see the flat surface of the pediment. You can also see the dip of the sedimentary beds. They're dipping to the east about 3 degrees, and the pediment is dipping to the west approximately a degree or less. So it's a small angle. These are valley fill sediments in the Ruby Valley, and they're a combination of hard and soft rocks. What formed these pediments eroded into a planation surface, hard and soft rocks the same, which takes a powerful current, because nature, or what we observe today, over millions of years, it'll erode the soft rocks into valleys and the hard rocks into ridges. So we should not see a feature like this. But the fact that it's eroded smooth and it has a capping of rounded rocks indicates water action. Here's one of the rocks I found on this pediment. It's well rounded by water. Some of these are kind of broken up as if the turbulence was so great it broke a lot of the quartzites. The big picture in this valley is a current channelized during the flood. We have mountains on the left and mountains on the right, to the east and the west. And the current was going down here at high speeds. And it was eroding the valley fill, which maybe was 2,000 feet higher, and it was just eroding and eroding it. And along the edges it forms these flat surfaces, and as the currents slow a little bit, the rocks that are doing the cutting fall down on it and form a thin veneer of gravel. You can see at the top of that it's only about 10 feet thick. When I talk about gravel, I'm talking about cobbles, which are about 2 to 10 inches, and then sometimes even boulders are found in this gravel. Now it's interesting that that there's about 4 or 5 hypotheses, uniformitarian hypotheses, to explain pediments. 4 out of 5 of them depend on water coming out of the nearby mountains. The thing is, those don't work because water coming out will dissect and destroy a pediment that's already there. Pediments aren't forming today. They're being destroyed. Like this canyon right here is destroying this pediment right here. And with time, this pediment will be gone. But they don't form pediments. So it's a unique feature formed by fast-flowing water down this valley, which was actually a channel from mountain to mountain sides, moving at high speeds and shearing the valley sediments off at an angle. Now, sometimes the pediment is formed in granite, and sometimes the mountains are granite, and it's like the pediments eroded along the edge of it to the point where it took out a chunk of the mountain along the edge, like a notch. It made a flat surface. There's lots of pediments like this, like in the Ruby Mountains of Nevada. So 4 out of 5 of the theories depend on water coming out of here, but that doesn't work. The 5th theory is by C.H. Crickmay, and he also discovered exotic rocks on a lot of pediments. I mean, this is not an unusual. I've seen a lot of exotic rocks like quartzites on pediments. They came from far away. He noticed that, and therefore he concluded that the water had to come from upstream going downstream, not coming from the mountains. But he said it had to be from some super flood. But to him, the super flood was an event that occurred every 900 years. But actually, if it was a flood like that, you'd have cut and fill terraces. You would not form a smooth surface. That's a smooth planation surface formed by lots of water moving over it and eroding it down, the water filling up the whole valley as a channel. Crickmay was on the right track, but because he was a uniformitarian geology, he didn't put 2 and 2 together and realized that during flood runoff, you could form pediments. And pediments we have them in Montana, especially southwest Montana and central Montana and a few places in north central Montana. We have them by several hundred of them. But you have them all through the Rocky Mountains, especially Arizona has pediments. Some of them are well over a couple hundred square miles. Now you can possibly confuse pediments with other flat surfaces seen along the sides of mountains, like alluvial fans. For instance, the famous Cedar Creek alluvial fan in the next valley over towards Ennis is an example, but that's a fan shape that came out from the mountain, a lot of debris, and that's a deposition where it deposited material. Pediments erode the rock down, like you can see the bedrock eroded down, and with only a veneer of maybe 10 feet of rounded rocks on top of it. So pediments are a lot different. Sometimes it's difficult to see. And over the world, there's probably thousands of pediments, indicating a worldwide flood. A water gap is a perpendicular cut through a mountain range or through a mountain, but it can apply to ridges and plateaus. Through the gap, a river or stream runs. Now there's also wind gaps. Wind gaps are actually passes in ridges and mountains where only wind goes through. And it was cut and eroded down to a V shape in general, but it didn't go far enough down to where the river can go through, so only wind goes through. The Shoshone Water Gap, the Shoshone River passed through that. It is 2,500 feet deep. These are the Rattlesnake Mountains that rose up just east of Yellowstone National Park. You can see the ridge on the left there. It's starting to go down, and within 2 miles, it drops down to the level of Cody. On the other side there of the water gap, there's a big low area. So the river, the Shoshone River coming east out of southeast Yellowstone Park, could have easily gone around the Rattlesnake Mountains, but why did it go right through the edge of the Rattlesnake Mountains in a 2,500 foot deep gorge or water gap? That's the mystery. It's a major mystery of geomorphology, but it's not unique. There are thousands of water gaps across the earth. There's approximately 1,700 of them just in the Appalachian Mountains alone. In the Zagros Mountains of western Iran, there are 300 water gaps, and these water gaps are as deep as 8,000 feet. Well, why do the rivers run through mountains and sometimes back out? That's the question. Now in North America, we have a number of prominent water gaps besides the Appalachian Mountains. In Western North America, we have the Green River that starts in Wyoming and heads for the Uinta Mountains. And when it hits the northern Uinta Mountains, it's deflected east, but in the process, it goes through a few ridges in water gaps. But then in the eastern Uinta, it cuts right through the eastern Uintas in a half-mile high slot canyon, when it could have easily kept going a few miles further and go around the Uinta Mountains at a much lower altitude. Why did the river end up doing that? And then when the Green River comes through the southeast Uinta Mountains near Dinosaur National Monument, it goes through an anticline, which is a domed up sedimentary rocks. It goes right through it, and then along the long axis, east-west long axis of the anticline, then back out to the south, when it could have easily gone around to the west of this. Why did rivers do that? This is not unusual. Another one is Hell's Canyon, where the Snake River should have went out into southeast Oregon and continued on to the Pacific. But instead, it takes a right-hand turn and goes through two mountain ranges, the Wallowa Mountains and the Seven Devils Mountains in Idaho. It's about 7,000 feet deep on the Idaho side. It's the deepest water gap we have in North America, and it's about 80 miles long. The deepest water gaps in the world are in the Himalaya Mountains. About 9 rivers start in the southern Tibetan Plateau and start heading down towards the Himalayas. And for a while, they're deflected by the structure of the mountains. Then after a short while, then they cut right through in major water gaps. For instance, the Arun River, A-R-U-N River, just east of Mount Everest, goes through a water gap that is 4 kilometers deep, or about 13,000 feet deep. That's probably the deepest water gap in the world. It's a major mystery of uniformitarian geology, and they're found worldwide. Can we explain it during the flood runoff? Indeed we can. As the waters were channelizing more and more, the water was going perpendicular to ridges that were either coming up or the water was lowering. Remember, the water was draining off the continents as they were coming up. And as it's going perpendicular to a ridge or a mountain range, there's low spots generally, and the low spots, the water will tend to funnel through there. And as it funnels through there, it'll tend to accelerate. It's like moving water through a wide pipe into a narrow pipe. The same amount of water, it has to accelerate through the narrow part of the pipe. Same thing with a water gap. You had a lot of drainage that was wide, it narrowed, and so as it narrows, it accelerates, and as it accelerates, the erosion rate goes up tremendously, and you cut the water gap rapidly. And then the wind gaps were early water gaps, but for some reason the water quit going through them and was funneled through what is now the water gap, and so it quit too soon. So the wind gap is left on the ridge high and dry with no water but just wind passing through. Well, after the flood, the rivers take advantage of those low spots and just drain right on through, just following after the narrow last bit of the late flood drainage. Now, what's the significance of these water gaps? Well, the uniformitarians have tremendous difficulty explaining why the river will cut through a mountain when it should have easily gone around. But in the retreating stage of the flood, it would be easy to form a water gaps as well as wind gaps, which are higher up on the ridge or mountain. It's easy and provides powerful evidence for the retreating stage of the flood. Well, the uniformitarians have trouble explaining this water gap. There's 5 hypotheses or theories. The one they apply is what's called the antecedent stream hypothesis, which means the stream or river came first and it was flat over here, no rattlesnake mountains. And then the rattlesnake mountains come up slowly and the river continues to erode through it slowly over hundreds of thousands and millions of years at the same rate, so that it doesn't deflect the river to the south or doesn't form a massive lake here because it rose too fast. We don't see evidence of lake sediments here. It'll cut 2,500 foot as it rises, so that's the one they apply. And the reason I believe that is because the Rattlesnake Mountains are young mountains. Supposedly the river was before the mountains rose, but there's no evidence of that, and it requires special conditions of uplift and erosion rate to accomplish this feat. Meanwhile, is tremendous. It's powerful evidence for the runoff of the floodwaters, and it also shows that when we have thousands of these water gaps, significant water gaps over the Earth, we had a global flood. Just like other features of geomorphology point to a global event, not a local flood. Now, if the Shoshone water gap was unique, the uniformitarian hypothesis would have more merit. When we have so many across the Earth, and you have to have special conditions of uplift and erosion at the same rate with hundreds of water gaps for just that hypothesis. Other hypotheses are applied to other water gaps. It really stretches the imagination to think that this hypothesis would work at all. And with so many water gaps, and you have to apply it worldwide, it's really a stretch of credulity to believe that. The flood can easily form water gaps as the floodwaters are draining during the recessive stage of the flood, and they're channelizing. They often will go perpendicular to a rising ridge. Like this Rattlesnake Mountains here was a rising anticline or ridge. And the water was probably coming from west to east, down from Yellowstone Park, and narrowed as a channel and cut that water gap going perpendicular. It's pretty easy for the flood to do it. During sheet flow erosion of the continents, the material moved off the continents to deep water along the edge of the continents and formed the continental shelf. And then, during the channelized flow phase of the flood, deep canyons were cut perpendicular to the shoreline in these continental shelf sediments. And Rock Creek here in the Beartooth Mountains is a great analog of what many submarine canyons look like underwater. There's actually thousands of submarine canyons. Most of them are on the continental slope. You have the continental shelf, which is very flat, that slopes slowly out seaward, and then you have the drop off of the continental slope. You have thousands of them. Mostly they're on the continental slope due to sliding and sloughing, but some of them are actually on the continental shelf. And they look like this on the continental shelf. In fact, the continental shelf would look flat, and then suddenly you have a deep canyon. The average submarine canyon is 3,000 feet deep, and we're about 3,000 feet above the bottom of Rock Creek down there. So this is be a great analog for what a submarine canyon looks like. And submarine canyons that indent the continental shelf, there's probably several hundred, maybe up to 1,000 along all the continents and off large islands. These submarine canyons, besides being an average of 3,000 feet deep, are an average of 50 miles long. Some of them are deeper than Grand Canyon. For instance, Zemchung Canyon along the Bering Sea Shelf is about 10,000 feet deep. There's a Cap Breton Canyon off northern Spain that's 10,000 foot deep submarine canyon, 3 times as deep as Rock Creek here. The formation of submarine canyons is generally a mystery to uniformitarian geology. And the reason is because the erosion's focused and it's on the continental shelf. In fact, some of these submarine canyons go almost up to the shoreline. For instance, Monterey Canyon in Monterey Bay. You have a submarine canyon that's a mile deep, the size of Grand Canyon. It starts near the pier at Moss Landing in Monterey Bay. In fact, if the submarine canyon moves backwards due to slumping, it's going to take the edge of the pier and crash it right down into the submarine canyon. The origin of these things, they used to think it was during low sea level during the Ice Age, but too much erosion, too focused in one narrow area. So now they're much older in their scheme, and I would agree with them. They actually have nothing to do with the Ice Age. I believe they happened during the channelized flow phase of the flood. After you form the continental shelf by wide currents depositing all that material, and it channelized off from a valley. The valleys on land focused the currents to speed up and erode material out of the valley that we see on land now, and deposited the material on the edge of the continental shelf, and that material started sloughing down. And when it sloughed down, it became like a turbidity current or a debris flow that sped up. And when it sped up, it eroded the canyon. And When it started to erode, more material focused in there, and it was like a chain reaction, and it deepened and deepened really rapidly during the channelized flow phase of the flood. And that's how submarine canyons, I believe, were formed in a matter of weeks and maybe a month or two, very late in the flood. It's one of the last features that formed in the flood because it's on the surface of the continental shelf and slope. It's after the continental shelf, which was early in the receding stage of the flood. We've seen evidence out in the field in central Montana, north central Montana, southwest Montana, and north central Wyoming for the retreating stage of the flood. We can break the retreating stage of the flood down to three main segments. First of all, the mountains rise and the continents rise and the valleys sink down, Psalm 104:8, and the ocean basins sink. And at that same time, the water's rushing off the continents, sometimes at high speeds, eroding sedimentary rocks laid down early in the flood. You had a lot of upward vertical tectonics, and this is what drains the floodwaters off. The sheet flow phase is from about day 150 to about day 250. When currents were very wide, there were very few obstructions holding the currents back. Very few mountains and plateaus had risen yet. They're in the process of doing that though. During this phase, while we had a lot of erosion, we planed the continents down as they were coming up down to planation surfaces. Sometimes erosional remnants were harder and they weren't planed down to a flat surface but were left as mounds or even vertical towers like Devil's Tower or Black Butte on top of the Gravelly Range. The third major part of the recessional stage of the flood was the channelized flow. As more mountains and plateaus became exposed above the water was forced to channel around them. And as it did that, it accelerated. And the currents probably were very wide and then they narrowed with time, probably from day 250 to day 371 approximately. And it depends on altitude. We had four major landforms that were formed that cannot be explained or are very difficult to explain by slow processes of erosion over millions of years of the Uniformitarian model. Number one, vertical walled canyons with flat bottom valleys. A second feature are pediments. We've seen a number of pediments here, but there's many more, hundreds in Montana, probably a couple thousand in the western United States and several thousand worldwide. The third feature is submarine canyons. And these canyons were formed after the continental shelf and slope sediments were deposited. They're perpendicular cuts formed in this. They're the size of Grand Canyon, a lot of them. A fourth feature formed during the channelized phase are water and wind gaps. Many landforms that are common all over the earth cannot be explained by slow processes of erosion over millions of years. A lot of us are bringing back the flood into Earth history. And you know something? We are finding solutions to many mysteries out there in the rocks, of which this series shows you mysteries from the field of geomorphology.